Hello everyone, welcome back to my YouTube channel. Today we are going to focus on voids in crystals. So as we know, the packing fraction of all the crystals is always less than 1. As we know, for FCC and HCP the packing fractions are highest and are equal to 74% or 0.74. This is less than 1. FCC is face-centered cubic and HCP is hexagonal close packing. So, what does this indicate? This clearly tells us that there are empty spaces between the atoms in a crystal, and this can be genuinely justified. Suppose this is your cubic crystal and there are atoms lying at the center whose center lie on the vertices of this cube. So, suppose this is your atom. When they are in contact, there is still space left between them. See this space. This is still left out. So this leads to the formation of voids. Because when these spheres are stacked, they cannot be stacked in such a manner that there are no spaces left between them, since at the point of contact there is only a point contact for spheres. There cannot be any line or surface contact. So these voids allow for interstitial alloying. What is interstitial alloying? Interstitial alloying is that a foreign particle or your alloying element, whatever element you are adding, that sits in these interstitial positions. Okay? So these are the interstitial positions. Now, the size and distribution of these voids dictates the solubility and diffusivity. That dictates the solubility and diffusivity. So, larger the void, larger will be the solubility of the foreign elements and higher will be the diffusivity. Because then the foreign element or the atom of the foreign element will have larger space to accommodate itself. Now, the position of these voids remain consistent with the symmetry of the crystal. Suppose, like cubic crystals have have four threefold rotational symmetries along the body diagonals. So these voids also have similar symmetries. Let us continue to the different types of voids in different crystal systems. Starting with the simple cubic structure. So this is, as shown, is the lattice with these red circles as your atoms on the lattice sides. So there will be a void at the center. Okay. So let us calculate the size of the largest void. So this void, if we see the projection along the body diagonal, the void will be like this. This is your atom, these black ones, and in the center is your void. Suppose the radius of the atom is RA and the radius of the voids are R void. So for a unit cell dimension of A, the diagonal of this face will be root 2A, like suppose this will be under root of A square plus A square, giving you root 2A. So for this body diagonal, considering this triangle ABC, this triangle, so if I draw it here separately, this goes on like this is the face diagonal, so this will be root 2A. This is the edge of the cube, this will be A. So this hypotenuse will be root 2a square plus a square under root. So this gives me root 3a. Now these atoms will be in contact along this edge length. So two radius makes one edge length. Now if we see along the body diagonal, this root 3a is equivalent to 2 radius of the atom plus 2 radius of the void. Now let us calculate. So if I replace this a from if I replace this a from equation 1, so I get root 3 into 2ra, that is equal to 2ra plus 2r void. So 2 and 2 cancels out from both the sides, and this leaves me with root 3ra is equal to ra plus r void. So this gives me root 3 minus 1 ra is equals to r void. Then the ratio of the radius of void with the radius of atom is root 3 minus 1. So this gives me r void by ra equal to 0.732. This is the final ratio. So coordination number of the simple cubic void is 8, because these voids ultimately make a simple cubic lattice. An example of simple cubic lattice is polonium, and it is the only element that crystallizes in a simple cubic structure. Let us move towards face-centered cubic. In a face-centered cubic crystal, atoms are in contact along the face diagonal. So, what is face-centered cubic first? For a face-centered cubic, the atomic positions are at the vertices of the cube and at the face center of each face. So since we have 6 faces, so there are 6 atoms at each of the face centers. So from this, we can see the projection along this line, along this face diagonal, where the atoms are in contact. So this length, this face diagonal is root 2a as calculated previously, like a square plus a square under root. So this root 2a is equivalent to 1, 2, 3 and 4 atomic radius. So root 2a equals to 4 atomic radius. So a is equal to 2 root 2 and into atomic radius. So this is your equation 3. So let us look at the octahedral voids first. So what are octahedral voids? The coordination number of octahedral void is 6. Okay. So as its shape is somewhat like this. So these are your atoms. This is your vertex atom. So this void is in contact with direct contact with 6 atoms, 1, 2, 3, 4, 5 and 6. So for a face-centered cubic, there is one octahedral void at the body center. By joining these, you can see the formation like here. Okay, and there are octahedral voids at each edge center that are shared among 4 unit cells. So these are formed by In one plane, there are these atoms, two face atoms and two vertex atoms, and then face centered atoms of the above and below unit cells. So this results in an octahedral void at the edge center. So what is the total number of octahedral voids in FCC then? This becomes 1 at the body center plus there are 12 edges in a cubic crystal, and there is one octahedral void at each edge center. So 12 octahedral voids, and that are shared among 4 unit cells. So in one unit cell, the contribution will be 12 by 4. So this gives us a total of 4 octahedral voids in FCC. Now, if the radius of the void is R void, then let us see here. Along this edge, length of A, there are 2 atomic radius and 2 radius of the void. So if you see here, this one, if you see here, there are 2 atomic radius plus 2 R void gives you A. So replacing A from this equation gives 2RA plus 2R void equal to 2 root 2 RA. Taking out 2 common, we have RA plus R void equal to root 2 RA. This changes to R void equals to root 2 minus 1 RA, and the ratio is R void by RA is equals to root 2 minus 1. So this is R void by RA equals to 0.414. This is the ratio of the void. Okay, so let us continue with the tetrahedral void in FCC or cubic closed packed crystal. Here, the coordination number of a tetrahedral void is 4. Since the void is in contact with 4 atoms, here you can see this green cross is the void and it is in contact with these 4 atoms. So, for a clear imagination, if this is a regular tetrahedron, the void at the center is in contact with these 4 atoms 1, 2, 3, 4. Now, let us see how many tetrahedral voids are there in an FCC crystal. So, here you can see 3 face centers and atoms and 1 edge atom together makes a tetrahedral void. And these voids lie at a distance of 1 by 4, 1 by 4, 1 by 4 from each of the vertex along the body diagonals. So, there are a total of 4 body diagonals in a cubic crystal, and each body diagonal has 2 such voids. This makes a total of 8 tetrahedral voids in an FCC crystal. So along the body diagonal, if we see, if this is the body diagonal, so one will be here. For another body diagonal, one here, one here. For another body diagonal, one here and one here. And for this last body diagonal, one here and one here. This requires a certain amount of visualization or imagination. Now let us see what is the size of the largest atom that can fit in the tetrahedral void in an FCC structure. So this is the tetrahedron drawn to scale, where T is the centroid of the tetrahedron and E is the edge length. So since it's a regular tetrahedron, all the edges are E in length. We, we assume that this void lies at the centroid. That is, the center of the void coincides with the centroid of the tetrahedron. So this dt length becomes a summation of atomic radius and the radius of the void. So from the triangle ABC, so this is your triangle ABC with each length as E. So this is AM. So this BM length is E by 2. Okay. So from here AM is equal to E square minus E by 2 square under whole under root. So this AM becomes root 3 by 2 E. So since AO is the centroid, so AO is 2 by 3 of AM. This implies AO has a length of 2 by 3 into root 3 by 2 E. So we get AO as E by root 3. Now let us look into triangle AOD, which is this triangle AOD. Let me make another clear view of this. So this looks like this AOD. This point is T. So AO has a length of, as calculated just now, E by root 3. AD is the edge of the tetrahedron, so has a length of E. And we need to calculate DO. So applying Pythagoras here, we get AD square is equal to AO square plus DO square. So AD square is E square is equals to E square by 3 plus DO square. This gives us DO square is equals to E square minus E square by 3, which is 2 by 3 E square. So DO is simply the square root of 2 by 3 E square, which gives us under root of 2 by 3 E. Now dt is 3 by 4 DO. So this becomes 3 by 4 into 2 by 3 under root E. Plugging in this value to this equation, which is summation of atomic radius and radius of the voids is equal to dt, we get Ra plus R void equals to 3 by 4 into 2 by 3 under root E. And we assume the atoms are in contact along the edge of the tetrahedron. This is so because, as you can see from here, this is one edge atom and one face center atom which are in contact in FCC. So replacing this value, we get Ra plus R void equals to 3 by 4 into root 2 by root 3 into 2RA. So cancelling out the terms, we get RA plus R void equals to under root 3 by 2 RA. So R void is equals to under root 3 by 2 minus 1 RA. So R void by RA becomes under root 3 by 2 minus 1, and this is equal to 0.225. So this is the ratio of the largest radius of the void to the atomic radius for tetrahedral void in FCC. Now let us continue to body-centered cubic crystal. For a body-centered cubic crystal, the atoms lie at the vertices and at the body center, and the atoms are in contact along the body diagonals. So this gives us that the length of the body diagonal is equivalent to 4 times the atomic radius. So if we see the projection of the body diagonal, so it has one complete atom and two half atoms. So this is RA, this is 2RA, and this is RA again. So this is root 3A is equals to 4RA. This gives us A equals to 4 by root 3 into atomic radius. So let us first see the octahedral voids in BCC. BCC crystal has distorted octahedral voids instead of regular ones. This means that all the edge lengths of the octahedral voids are not equal. So here we can see we have one octahedral void at the face center, and it is shared by two unit cells. So what are the contributing atoms? We have 4 atoms of the vertices and 2 body center atoms that together make this octahedral void. Okay. Next is we have one octahedral void at each edge center, and that is shared by 4 unit cells. So we can see these 4 body centered atoms along with these 2 vertex atoms this way. Make one octahedral void at the edge center that is shared by 4 unit cells. So let us see the total number of octahedral voids in VCC. So one at face center, total there are 6 faces and each is being shared by 2 unit cells. So 6 by 2 plus we have one at each edge center. There are 12 edges in a cube and each is shared by 4 unit cells. So divide by 4 for per unit cell. So we get a total of 6 octahedral voids in BCC. Now let us look at the size of the largest atom that can fit in the octahedral void of BCC. So this is as shown is the octahedral void, and since it is distorted, these 2 body center atoms are at a distance of a apart, and, this void is in direct line with these two atoms. So we get twice the atomic radius plus twice the radius of the void is equal to a. And for BCC, a is equal to 4 by root 3 RA from above, from here, 4 by root 3 RA. So we get, cancelling out 2, we get RA plus R void is equals to 2 by root 3 RA. So R void is equals to 2 by root 3 minus 1 RA. So R void by RA is 2 by root 3 minus 1, and this is R void by RA is equals to 0.155. So this is the ratio of the radius of void to atomic radius for octahedral void in BCC. Let us move towards the tetrahedral void in a BCC crystal. Similar to octahedral void, here also the tetrahedral void is distorted and not regular. Each surface of the BCC crystal has 4 distorted tetrahedral voids that are shared by 2 unit cells. So, 2 body-centered atoms and 2 vertex atoms contribute towards one tetrahedral void, like this. So let us see the total number of voids, tetrahedral voids in BCC. So 4 on each surface and a total of 6 surfaces. So 4 into 6, and each void is shared by 2 unit cells. So by 2. So this gives us a total of 12 tetrahedral voids in BCC. Now let us look at the size of the largest atom that can fit into the tetrahedral void of BCC. Let us consider this tetrahedral void formed by 2 body-centered atoms and 2 vertex atoms. This one, as shown in this image. Okay. So here, in triangle OCM, that is shaded in green here, OC is given as OM square plus CM square whole under root. So this is your OCM triangle, OCM, this is perpendicular. OM is A by 2, whereas CM is A by 4. So OC is equal to A by 2 whole square plus A by 4 whole square and complete under root. So this is A square by 4 plus A square by 16. This is 4A square plus A square by 16 under root. So this is root 5 by 4A. Now OC is equal to atomic radius plus radius of the void. So we can have root 5 by 4A equals to RA plus R void, and for BCC A is equal to 4 by root 3 RA, which becomes equal to RA plus R void. So the equation is something like root 5 by 3 RA equals to RA plus R void. So R void is equals to root 5 by 3 minus 1 into RA. So R void by RA, the ratio is under root of 5 by 3 minus 1. So R void by RA is 0.29. This is the required ratio. Now to summarize the entire thing. Let us make a table. Crystal, void type, number of voids per unit cell, and R void by RA ratio. Okay. So for simple cubic first, we had seen a cubic void where there was only one void per unit cell and the ratio was 0.52. Next we had was FCC or cubic closed packed crystal where one was octahedral void where number of voids per unit cell was 4 and the ratio was 0.414. And for tetrahedral, there were 8 voids per unit cell with the ratio being 0.225. Last was body-centered cubic with distorted octahedral, this being 6 voids per unit cell with a size of 0.155, and tetrahedral, these are also distorted and 12 in number per unit cell with a size of 0.29. So this way we can summarize. Okay. Thank you all for your attention.